Hello, my name is Chance Hattrick, and this is my 4517 grade code to 7 segment display encoder. So you can see here that I'm currently displaying a value on my 7 segment display as a 0, representing the grade code value of 0. Now by turning this grade code encoder clockwise, I can then increment it by 1, as you can see with these LEDs here, and represent the appropriate grade code value on the 7 segment display. Which allows me to represent 16 gray code values through the use of logic gates. Over the course of this video, I will explain how I was able to simplify the logic required for this circuit through the use of binary postulates, minterm, maxterms, and K-mapping. K-mapping works on the principle of minterms and maxterms. Minterms and maxterms are essentially the maximum number of combinations variables can be in AND or OR logic for an output of 1. Each function may not use all of the minterms, but they must use at least one. You see with minterm 0, you can see that minterm, if you take the AND of the complement form of each of the 3 variables, you would get an output of 1. Unlike that, for maxterm 0, if you ORed the normal form of each of the variables, you would get an output of 1. Normal form in our case represents the value 1, and complement form represents the value 0. By using minterms and maxterms, you are able to effectively simplify and read out the logic for any type of circuit. This is especially useful for K-maps, where you can use a sum of products to create a simplified logic circuit for any circuit. In our case, it's the 4517 gray code to 7 segment display circuit. Now here's our 7 segment display, and here's the segment being analyzed in the K-map table. Here we're having segment A. You can see on the table in the subscript I have labeled the value that each of these cells represents. So you can see for value 0, segment A is on, and for value 1, segment A is off. Now I could technically take the minterm for each of these individual cells. So for example, for this one here, the minterm would be D0, C0, B0, A0. However, this would require a large number of gates, a large number of chips, and a large amount of time. So to simplify the circuit, I can take adjacent ones of each other and eliminate the variables that do not have an impact on the output. For example, for these red squares here, you can see that the B and the D do not have any impact on the output of the 1, as they can be in complement or normal form without having the value be turned to 0. So this gives me a simplified minterm of C0, A0. Similarly, for the purple square, I can do a similar thing by eliminating variables D and A. I can do this 2 more times with the purple and the blue squares, and you'll notice that I have one final 1 that is not easily placed in a group of 4. For this, I take a group of 2 that eliminates at least one variable, in this case variable A, which gives me a minterm of D0, C0, and B. Now you may see here that this is much more simplified than if I had taken the minterm of each of the individual cells. However, this would still take a large number of gates to execute, as each of these AND gates needs to be done individually as well as the ORs. To simplify this even further, I can use the binary postulates. Here, these are laws that are taken from algebra that allow you to simplify binary expressions. Particularly, I'll be using the distributive law, or postulate number 4. Here is the result of using these postulates along with the simplified K-mapping to give the final logic for each of the segments. You can see for segment A, I've used the distributive form to eliminate the need for at least 4 AND gates. You can also see here that I have highlighted certain minterms, and that's because these minterms occur multiple times throughout the circuit. So I can eliminate further amounts of gates by simply taking the output of CA and using it as the input of the other segments. By using these minterms, K-mapping, and postulates, I am able to effectively eliminate and simplify the segment logic for this circuit, allowing me to create a circuit that is as efficient as possible. I could simplify the circuit even further if through the use of XNOR gates and XOR gates.